This week, we're going to take soil temperatures from the Oklahoma Mesonet, parse them out, create some human-readable labels, and create a violin plot like this, which is a very easy way to visualize not only the data, but some statistics surrounding it. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to talk about a violin plot. And this is a plot that I personally wasn't that familiar with until recently. If you go pull up the Wikipedia article on it, you can get a nice summary of it, but the basic idea is this is a box plot that is a lot more informative because instead of just showing you the extremes and the quartiles, you can actually get the kernel density estimate plotted. So think of it like a histogram plotted along the vertical axis of the data here. So you can see how spread out or how condensed is my data and get an idea of what that really looks like. So let's make one. I've downloaded a file from the Oklahoma Mesonet, which is soil temperature data. And so we've got temperatures at different depths in the soil, for example, 5 centimeters or 60 centimeters. And averages over 1, 3, or 7 days. So we could plot this up and see what these different averages look like. Are they more spread out? Are they more condensed? Do the temperatures become more uniform with depth or more uniform towards the surface across the state? So let's read this data into a notebook. To do this, we're going to use pandas. We've talked quite a bit about pandas in the past, including reading some Mesonet data, if you want to go look at those past MetPy Mondays. We're going to import matplotlib and numpy, and use our matplotlib inline magic so that our figures plot in the notebook. So now it's time to read the data. We're going to use the pandas read CSV functionality. And the file name is going to be latestrecentsoil.mdf. If we just run that and look at the data frame, that's probably not what we were expecting. If we go back and look at our data, we see we have 2 lines of header to remove, and then we've got our column names, and then this white space delimited data. So I'm going to skip 2 rows, delimit based on white space. And I'm also going to go ahead and set any null values or any minus 999.000 in the file to be nans. If we don't do that and make these plots, we'll see that a bunch of negative 999s really stretch the plots out and make them not useful. So instead, we're just going to change those to be not a numbers or nans. And that should be in a values. There we go. So now if we look at our data frame, this looks quite a bit more like what we were expecting. Each row is a different station across the state, so we're going to be making these violin plots that summarize the statewide soil temperature. Now I'm going to remove any rows that have nans because we don't have all the information for that site, so we can get rid of those. I'm also going to remove columns that we don't need. So I'm going to use drop NA. The in place equals true. That means we won't have to reassign df. So we run that cell. And then I'm going to call df.drop, provide a list of columns that we don't need. So station ID, station name, the time column, we're not going to need that, as well as a few of these columns that I don't want to plot statistics for. So we've got 1, 3, and 7 day averages there. All right. And again, so I don't have to reassign, I'm going to use in place equals true and axis equals columns as we're dropping columns, not rows. All right, so let's look at our data frame again. All right, so we can see that we've got temperature soil at a few different depths, averaged over 1, 3, and 7 days. That's a good start, so let's go ahead and try to make a plot. I'm going to create my figure and axis using plot.subplots. And we are going to call violin plot. You can call violin and specify all of the individual attributes of violin to get an individual one, but violin plot will work on our data series that come out of this data frame here. So there we go. We've got a reasonable plot already. Now you notice a couple things. For one, we don't really want numeric indices here. They don't mean anything to us. We also got a bunch of poly collections back. So I'm going to assign the return of violin plot to underscore so we can not see all of that. But I want to set these tick marks to be something meaningful, labels that have a human readable name. So let's figure out how we're going to do that. I'm going to insert a cell, and I'm going to create a function to parse variable names. So I'm going to define my function, parse variable name, and it takes a variable name. Remember, the next line of any function should be a docstring. It can just be one sentence, but you need to leave yourself or whoever is reading your code in the future a note of what this function does. So it makes a readable name from the Mesonet variable name. I'm going to put a cell in above here. I'm going to make it a markdown cell. So this has no functionality on the code, but it's going to be a nice note to myself. So variable name examples. And I'm going to go grab a couple example variable names here, just so we can see right above where we're writing this function what we're trying to break down. And if I run that cell, it renders nicely. Okay, so I think the first thing I'm going to do is split the variable name apart into the two components that I really want, which are the depth and the length of the average. So I've got a depth of 25 and a 7-day average, or a depth of 5 and a 1-day average. To do that, I can split based on the characters AV. So I'm going to call split based on the characters AV. So let's print var name, and let's call our new function with one of our example variable names. Okay, so it's split into the two parts. Good deal. Now we need to work with the first part, remove the TS and make this an integer, so we can remove that leading 0. We don't really need it. And then the second part, we just need to remove the D. There are several ways that you could do this, but I'm going to say depth is going to be integer of the first part of our split there, so the TS 05. And then I'm going to call dot replace TS with an empty string. So this will take the 0th element of that list, TS 05, replace TS with an empty string, so we'll just have 05, and then cast that to an integer. For average, the length of the average, we will call the 1th element of the variable name, which is 1D in this case. And I'm going to replace D with nothing. There are several other functions you could use here as well. Strip would be a good choice. You could strip TS, strip D. You could strip all non-numeric characters. There are many ways you could do this. This is just the way that I've decided to do it. And now I'm going to return a string that is my human readable name. And for that, I'm going to use an F string. Again, these are Python 3.6 or later, but I highly encourage you to use them. So in curly braces, I'm going to put the name of the variable that I want, depth. So it's going to be a depth centimeter. the variable average, day, average. So now we get the string back 5 centimeter, 1 day average, which is a pretty human readable name. So now we need to call this function on every column name or every data series name from our data frame, and then set those as the tick marks. Again, I'm going to put another cell in, and I'm going to use a list comprehension to create those labels. We've covered list comprehensions before. These are a really nice way to condense a simple for loop into a one-liner. So first we put what we're going to append to our list, which is the output of our parsed variable name function for some variable name in, and then what we would normally use as a for loop. So for in df.columns. So this says go through df.columns, iterate through it, assigning each thing in each iteration to a variable in, pass that to parse local variable name, and store its output in a list. And we will do that for all elements in df.columns and call it labels. So let's look at labels and verify that it did what we thought. And that looks pretty good. Okay, so let's try setting our tick labels and see if we get what we expect. So I'm going to call the set x tick labels method with labels. Well, it's hard for me to tell exactly what's going on, so let's rotate those. And I'm going to assign its output to underscore as well. Okay, well, that's not exactly what we were expecting. It took each of those and assigned them to a tick label, but we're not ticking every single one of these. So these are ultimately incorrect. Let's go back and look at the documentation for violin plot. Positions sets the positions of the violins. Ticks and limits are automatically set to match positions, and it is an array. The default is 1, 2, and so on to n. Okay, so let's set the ticks. So on X, we're going to call set x ticks. And let's say we're going to go an array range for the length of df.columns. So take however many things there are in df.columns, and we're going to make an array and set our ticks to that. Okay, well, we're closer, but we're not there yet. Remember, in our violin plot documentation, position started with 1, whereas here things are starting with 0, 1. So we're shifted to the left 1 position from what we should be. You could deal with this in a few ways. So you could set to start at 1, and you could go to the length of df.columns plus 1. Remember, it goes up to but not including, and that would do it. That's the easiest way. You could also go from 0 to the length of df columns plus 1 and insert an empty string as the first element of your labels list, but that would require 2 lines of code, and I think this is quite a bit clearer. It also starts at 1, just like the positions of our violins. So there we go. With not a whole lot of code, we've created a nice violin plot for every column in this data frame of soil temperatures that we were interested in. And we can start seeing things like, where do we have a wider spread in the distribution? Down here at 60 centimeters. What about in the upper, the 5 centimeter soil temperatures? Well, it looks like the 1 day is clustered much lower than the 3 and 7 day averages. So we can tell something about what the local temperatures have been doing. And we also see the 10 centimeter 1 day average has this interesting cluster closer to 10 degrees with a very long tail. So it's fun to look at your data like this, and certainly a lot more informative than a simple box plot of the data. And as you see with Matplotlib, it's relatively easy to make. I hope that you found this useful, and I'll see you on next week's MetPy Monday.